Okay, here we are again. So here we're reviewing mission 9 of Stat E100. And I actually like this week because this week we actually played the role of my home discipline, actually. Even though I published in psychology and public health and worked with psychologists, as you would as a statistician, I'm actually a sociologist. This is my confession. And sociology is a really exciting field. It's quite broad. And we're going to cover quite a bit of material on contingency tables this week. And as I was just saying before I started the recording, of course, we have this mission, and then we have next week, and then we have the review of the entire course. And we have the final exam on December 17th. So I want to emphasize we do have time. We also have time for the papers, final projects, and I encourage you to meet with the staff, meet with me, meet multiple times. We're all here to help and address particular concerns. But our goal today for the next hour is to understand the concepts behind this is essentially this week, and with the focus on mission 9. So that way you can understand how you got those particular answers. And as I said previously, when we talk about the second half of the course, which focuses on inferential statistics or statistical inference, I apologize. Let me make sure we focus on me. Do you guys, if someone could text, do you know if you actually see me in the video? Otherwise, I might actually turn that off. I see myself now. Okay. You should be able to see me. Okay. I know some weeks you might not see me because it's sometimes we have bad connections, but okay, good. See some chats here. Great, thank you guys. Thank you everyone. All right. So this week, as I said, in the second half of the course, we essentially think of it as a revisit of the first half of the course, except now what we're doing is we're just taking this idea that we're going to take move from description, which is localized. We describe the sample at hand, to inference, which means what can we say about this sample with regard to the larger world and the larger population. Of course, I know I'm beating this, drilling this through, but I think that is how I understand the second half of the course, and I think it's a way to recognize that this isn't entirely new. So the analogous week for the week on contingency tables was the week that we focused on when we looked at the GSS data sets, and we looked at health and the probability of being in poor health or healthy if you're in poverty or not. And we had contingency tables and we looked at relative risk. Well, now we're essentially doing this with a statistical test of inference called the goodness of fit test. But we're using a different data set, of course, as we usually do, because we want to also introduce you to different types of data. So I'll just kind of walk you through this homework assignment with an elaboration of the concepts that I think are important for learning the material, the statistical material. As you'll see with some of the answers, you'll see a little bit of description in the assignments. Hold on for a second. I apologize. I had to make sure that my internet cable was connected. Okay. So in this week, as a sociologist, we're going to answer one question that sociologists often answer. Hold on for a second. Someone asked, is there a mission 10? If you look at the course syllabus, we actually don't have a mission 10, but we do have a week 10. And we will include material in that week. So for that week, in essence, we cover the course material. If you look at the module, actually, you'll see it. If you click on that module for that week, you'll see that it's we're going to focus more on the final project as opposed to the assignment itself. And in that sense, it's a little more free-flowing, but I will address the concepts for that week. And then I will also address and revisit some of the key components for the final paper project, which is of course something I did in an earlier week, about 2 or 3 weeks ago. So long story short, no mission 10. This is the last mission that you've done, so congratulations at this point. But there is a week of material that we're definitely going to emphasize and learn. And then after that, we also have a course review. And as I said before, don't be worried about meeting me multiple times at least. I can offer that to you. So let's go through mission 9. So our mission this week, as a sociologist, our goal is to answer this question: how do people's view of Wall Street executives differ based on social class and on other variables? Right, so how do our attitudes vary by social class and whatever else we're interested in? You can see this is pretty related to other fields, like when we looked at attitudes towards science or different disciplines. And we're taking the Wall Street data set. If you recall, in this week, we also have something called the TOY ANOVA data set. And we don't emphasize analysis of variance for the course, and we don't test you on this, but we do provide analysis of variance so that that material, so we do provide information on and code for understanding analysis of variance because it's important and it's relevant. But we had to cut out something for the sake of this course because we want to cover the material thoroughly. That being said, I think when you cover the concepts for tests of contingency tables, you are actually acquiring the knowledge or to interpret and understand analysis of variance. So when you encounter that, say, in another course or when you read another paper, you'll see some similarities there. But right now, we'll focus and drill down right on these tests for contingency tables. Okay, so how do people's view of Wall Street executives differ based on social class and other variables? We're going to analyze a Wall Street data set. It's a random sample of people living in the United States. So here's the goal of inference, right? We don't want to simply describe the sample at hand. We want to know what Americans think about Wall Street executives. And that's where inference comes in. So we can't just describe the sample and make a conclusion there. So as usual, you'll see some wrong answers that I typically put in. And in these later weeks, you'll see a couple answers that I used with code. You don't have to really emphasize or understand that, but let's just go through this in order, and I will elaborate on this. And if you have questions about any particular one of these, if you have a question about any one of these problems, then I skip ahead to that. That being said, I will say it takes a little bit longer to go through this week, but I'll try to go as quickly as possible. And I say that because on Monday when we reviewed the code, I think I went 30 minutes over, and I apologize. So let's go with question 1. You gather a random sample of 200 people and ask them whether they disagree or agree with the following statement. Quote, the tax rate on billionaires should be increased. Very appropriate given a lot of the debates in the United States about the tax plan that is pushing through a decrease on tax rates for billionaires. Well, in our sample of 100 people, agree. 100 of those agree, 40 disagree, and 60 neither agree or disagree. So there we have the breakdown. So we just want to ask you what the proportion of a sample who responded to the answer disagree. Please round your final answer to 2 decimal places. Well, this is pretty much a give me question. That's why it is a half point. It's a reminder that what a proportion is and how you estimate a proportion. Well, in this case, a proportion, the correct answer is 0.20, and the R code will do it for you if you want to use the R code as a calculator, and that's what I showed in one of the R tutorials. But essentially, a proportion is you take the number of those survey participants who answer the question, who respond to the answer disagree, which is 40 right here. and you divide that by the total sample, 200. That's it. The rest of these look like they are answers that for the other breakdown. So 0.5 would be for those who agree. 60 looks like it would be correct if we wanted to look at neither disagree or agree. So there you go. Very simple answer. And we're going to build on this idea of a proportion. So based on question 1, what is the proportion of those who respond answer with neither disagree or agree or disagree? Well, same concept, except now we're going to use 60 divided by 200. Pretty simple, I hope. It's just the same concept. Now, we're going to talk about this idea of inference, and often in a one-way test of a goodness of fit, we're going to do what we've done in the previous weeks, which is we're going to test whether an assumption that we make about the purported distribution of proportions in the population is true. So we're going to test the hypothesis that that we have, and this is a one-sample goodness of fit test. And I think by following this example and explaining the answer, I think we'll kind of get to that. So, but first, I'll read the question. Based on previous research, you think that the distribution in the population is 0.5, 0.25, and 0.25 for agree, disagree, and neither agree or disagree, respectively. I want to key you to something. When we talk about distribution here, when we talk about categorical variables, we're not talking about the continuous distribution. That has a nice curve there. We're actually talking about the simple breakdown of categories. So we will sometimes use that word distribution to talk about different proportions or different average levels by 3 or more categories. So given what we know about our sample described in question 1, what is the expected count of sample participants who responded with the answer agree? Round your final answer to 2 decimal places. So this is where we get to this, we're kind of directing you pedagogically to this idea that a goodness of fit test compares what you would expect the count to be for in a given sample, given the distribution of proportions you would expect to be in the population, compared to the actual proportions. And the larger the discrepancy between the expected counts and the actual counts, the greater the likelihood that the hypothesis does not accord. The greater the likelihood the hypothesized distribution is not true. Right? It's sort of like, I know that might sound a little confusing, but just keep in mind when we talk about goodness of fit, the reason we talk about goodness of fit is we're basically comparing what we expect and then what the data show. How good do the data really fit to our expectations? That's kind of the intuition behind goodness of fit test. And I think it's important to remember that because there's a reason we call it that. And our tolerance for how good the data fits to our expectations leads to our conclusion about whether or not we have good reason to believe that our expected distribution is correct. So that's it there. All right. So now we're going to sort of talk about expected counts given proportions, and this is going to be on the test. So if we give you a proportion, and we give you, say, a sample size, then we want you to be able to calculate, or estimate, you should say, calculate the expected count if you know the proportion and you know the sample. Well, we know the sample from question 1 is 200. We know that the expected proportion the expected proportion of participants who responded with agree is 0.5. So to answer the question, we multiply our expected proportion by the total sample. That's 0.5 times 200. And that's what the code shows. And there you have a more, perhaps a more concise sentence. The expected count of sample participants who answered agree in the sample is 100.00. The following R code provides syntax. Right? So if you want to basically use R code as a calculator, there you go. And I'm going to expand on this a little bit more. If you had any kind of proportion and any kind of n, and you wanted to know the counts, then you will always multiply the proportion by the total n. So if I told you in a sample of 1,000, we found that 0.10 of those of the 1,000 respondents said they were unhappy. What is the count of survey participants who reported being unhappy? Well, it's simply 0.10 times 1,000. So there you go. The main point is plugging and chugging, and you can use the language of expected counts as we do here, or you can also use it to provide counts of the data at hand. Now, here we get to some output here that is important for interpretation within the R environment. I think it's also a good example of perhaps how you're able to present the output in your final papers. I said to I had reviewed some students' papers, and some of them asked, well, do we need figures? Should we write it out? I think it can be okay to provide the R output if you can provide it in a concise way. If you look at published papers, they will not provide the raw output. So if you're enterprising, I would encourage you to create the tables. But sometimes the raw output is good enough. And when I reviewed the syntax, I emphasized the fact that the output is pretty self-contained. It's a nicely done presentation of the data. So let me read you question 4. After running the one-way chi-square goodness of fit test and plotting the chi-square test statistic on the chi-square distribution with 2 degrees of freedom, you obtain the following results. Now I'm going to stop right there before you look at this output here, even though I kind of want to emphasize that it's okay to present. Remember, I said that we were talking about a one-way chi-square goodness of fit test. There's a one-way chi-square goodness of fit test, and there's also either what is often just called a chi-square goodness of fit test or a two-way chi-square goodness of fit test. Now, when we talk about a one-way chi-square goodness of fit test, what we are talking about is a test of our prior hypothesized proportions in the population. So one-way chi-square goodness of fit test requires us to have some idea or some hypothesis regarding the expected proportions. So as sort of to key you off when you're taking when you're going through problems, if we're ever saying a famous researcher hypothesizes or believes that the true population proportion distribution of beliefs is 0.5, 0.2, 0.3, then keep in your mind that that is actually the appropriate test is the one-way chi-square goodness of fit test. So that's the first thing. And now if we talk about a chi-square goodness of fit test or two-way chi-square goodness of fit test, we're actually talking about something different, which is do the proportions within two categories, are they independent of each other? And we'll talk about that later, but just keep in mind, this is different than that. Now I'm going to talk about another point here, conceptually, because I think the goal here is not just to answer the question or give you an answer, but actually to understand the concepts that are relevant for the course and for doing well on the exams. A chi-square is literally a statistic, and I'm going to show you this. This is what a chi-square will look like. It looks kind of like an italicized X. It's actually, that looks like it could be an italicized X. Technically, it's a little bit larger. It's a nice little spiral Greek X. And this is important when you're looking at the data, because in the output, you'll see an X here, an X squared here. That is actually refers to chi-squared. It's because the output is in the Latin alphabet. So keep in mind, often, not often, but sometimes when you see an X squared, and then in reference to some statistic, keep in mind you're talking about a chi-squared statistic. And I would say in the paper you can write chi. I would be okay if you wrote chi-squared. There should be a D, I would say, there actually in this question, which I actually haven't noticed after teaching this for several years. I think you're okay. A chi-square goodness of fit test is actually correct. I apologize. So we do the chi-square goodness of fit test. The logic here is to test whether the proportions that were believed to be true actually exist, that are actually likely given the data. And here, if we have a statistically significant p-value, then we can reject the hypothesized distribution of proportions. Because we have a p-value that is not statistically significant, we fail to reject the null hypothesis that the true population proportions that we'd expect are 0.5, 0.25, and 0.25 for disagree, neither disagree, agree, disagree, and neither disagree. In other words, what we believe to be true about the population, we cannot disprove that statement. Notice how I worded that again? It's because when you talk about a one-way chi-square goodness of fit test, the null hypothesis is that the true population proportions are what we have described. If we reject the null hypothesis, then what we're saying is that the data that we observe compared to that we expect is quite discrepant, which means that what we hypothesize to be true in the population is not necessarily so. So here, when you reject the null hypothesis, you're actually rejecting the hypothesized distribution of proportions. I'll say that again because I want to emphasize this. When in a one-way chi-squared goodness of fit test, when you reject the null hypothesis, you are rejecting the hypothesized proportions that we had believed to be in the population. Now, there are a couple of things here. When you reject what we have believed to be true, all we're saying is that what we had believed to be true isn't true because the discrepancy between our data and what exists in the population is too great, it doesn't match up. And now, here's the issue. If you reject the null hypothesis, typically we talk about accepting the alternative. Well, unfortunately, when we reject the null hypothesis, it doesn't necessarily give us certainty about what the alternative hypothesis is, because it is really a statement about rejecting the null, not about affirming the alternative. And in fact, in this case, we don't have a clear definition of the alternative except what we observe in the data at hand. So I'm going to drill down on the output here. What I want to emphasize here is that if you think this is a sort of a jumble, an assemblage of just numbers, keep in mind when you look at the output, this first line here Tells you exactly what's going on. It's a chi-square test for given probabilities, which is to say it is a one-way chi-square goodness of fit test. Data X, don't worry about it. It's a different concept. But the most important information is what you're seeing right here, which is this. I'm going to actually even highlight it if we can. No, it'll highlight the whole thing because it's the output. It is the fact that it is that second line under data, which is what you're going to see when you see published research. You're going to have a test statistic, you're going to have degrees of freedom, and you're going to have a p-value. All three of those aspects of your statistical output are related to one another. In other words, the chi-squared statistic and the degrees of freedom together tell you your p-value. So the reason we use the p-value, include the p-value, is it is essentially the clearest, most standardized form of comparing test results. So whether or not you do a t-test or a chi-squared test, they both produce p-values to make judgments about whether or not a given hypothesis is true. So here we have a chi-squared statistic, but we also have this idea of degrees of freedom. Keep in mind that the degrees of freedom is 2 here. So, and in previous weeks it was 1, because the way that you essentially estimate the chi-squared statistic, because we have more categories, we actually have 2 degrees of freedom. And the reason we have 2 degrees of freedom essentially taken away is because we have 3 categories here, right? So to know what the degrees of freedom for a chi-squared test, one-way chi-squared test, all you need to know is the number of categories. Say if we had 5 categories, you take away 1, then you have 4 degrees of freedom. Whereas when we did a t-test with of 2 means, difference between 2 means, we had 1 degree of freedom, and with a test of difference in proportions, we had 1 degree of freedom. I don't worry too much about degrees of freedom in chi-squared tests, although they do tend to be misreported if you look at the scientific literature, because people will just type them in and those kind of errors happen. Because it's just sort of in a way it's a convention. It's a way to sort of describe and convey to the reader what's going on, and you should know the math behind it. But then beyond that, it's really about the concept. And the reason we have to report the degrees of freedom, in addition to the chi-squared statistic, is both of those pieces of information tell us what our p-value would be. And here we have a p-value of 0.13, which is higher than 0.05. So it's not statistically significant at the 5% level, at the 0.05 level. And that's what our figure on the right shows. It actually shows the chi-square distribution, and it shows that where the data provide our probability of a type 1 or a type 2 error. And in this case, a type 2 error. And a type 2 error here would be, what is the probability of the null hypothesis being true, given that we rejected the null hypothesis? Sorry, type 2 error, sorry. We almost always have a type 1 error, which is a false alarm, which is rejecting the null hypothesis when it's in fact true. That's more often the case, the problem, because scientists are always looking for statistically significant results. A type 2 error is the failure to reject the null, which is what we have here, given the null hypothesis is true. So this right here, the blue here, is our probability of failing to reject, of essentially, hold on, failing to reject the null when in fact the null is true. And it's still a relatively small likelihood, but it doesn't meet our statistical threshold, our statistical convention. And Generally, if you look at most published papers, we won't graph the probability distribution. In fact, it's kind of redundant. But I think it's a good visual aid, especially for you, and it's good for an audience if you want to convince them of the results. Now, the last part here dissects the logic of the chi-squared goodness of fit test, which is, as I said before, even though we're dealing with categorical variables and we're talking about proportions, the chi-squared goodness of fit test tells us how, first estimates the counts that are expected given our hypothesized proportions, then compares those counts to those that are in the data, estimates the discrepancy, which is the residual, the contribution to the chi-squared distribution, and then tells us whether or not that discrepancy is large enough for us to think, and this is probably not a true hypothesis. Typically, when you see the results in science, you're not going to see this output here, but I think it's useful for our knowledge and for understanding, the data here. I think that's all I really want to say here, except intuitively, you don't even need the statistics. I think if you look at this, you can see the observed counts, given our proportions, are 100, 40, and 60. The expected is 150 and 50. Our intuition kind of tells us, well, these aren't too different. You can eyeball it. But again, when we talk about statistics, we don't want to just eyeball results. We want to have standardized criteria so that way we can contribute to a larger body of knowledge and have others look at it in the same way. Right? So that's the difference between guesswork and the rigor or the logic of statistical inference. I know I'm talking quite a bit about one question, but I hope these are helpful for understanding the final concepts for the weekend as you move forward in your statistical careers. And I think these will also lead us to answer the next questions relatively quickly. Based on what you know about from the above results, what are the number of categories K used to compute the one-way goodness of fit test? Round your final answer to 2 decimal places. First, I want to tell you, we often use K to talk about the number of categories. You'll see that quite a bit. And when we talk about categories K here, we're talking about the number of categories in the variable, in our categorical variable. Here we have 3. When we talked about the attitudes toward whether or not a scientific degree or a discipline was scientific or not, we have 2 categories K. And I already told you the answer. The number of categories K, based on the output, is the number of degrees of freedom plus 1. I don't think there's anything else to say there, except that's essentially how you do it. 2 might be confusing because those are the number of degrees of freedom. 1 is what you would subtract. 4 we threw in there just because who knows if you're guessing. But essentially, just keep in mind, if you had 5 categories, we might ask you, what are the degrees of freedom when you have 5 categories in a chi-squared test of given probabilities? Well, your answer would be the number of degrees of freedom would be 4. I don't think there's anything else to say there. And then there's a more elaborate explanation for the chi-squared for the one-way goodness of fit test. The degrees of freedom is df, which equals k minus 1, where k is the number of categories. Given the results show the degrees of freedom of 2, the correct answer is 2 plus 1 or 3. All right. How do we phrase our hypothesis? Our null hypothesis, as I said before, is the assertion that the proportions that we hypothesize are true. That the proportion of the first category is 0.5, the proportion for the second category is 0.25, and the proportion for the third category is 0.25. That's the null hypothesis. And for your final project, I think it's okay to write it out like that if you want to have a formalized hypothesis. And so just so you know how to verbalize it when you talk about this, to state this, you would say the null hypothesis, or H naught, O is often referred to as naught, N-A-U-G-H-T, is P of 1 equals 0.5, P of 2 equals 0.25, P of 3 equals 0.25, where P of 1, P of 2, and P of 3 are the proportions of the 3 categories we have for that variable. And of course, if we had 5 categories, we'd go all the way up to P of 5. Okay. Now, based on what we know from question 5, what is your conclusion at the alpha of 0.05 level? Well, zoom in on that. 0.1353 is definitely higher than 0.05. So at the alpha 0.05 level, we fail to reject the null hypothesis, which means that we can say that the null hypothesis is consistent with our data. Notice I keep talking about consistent with our data. I'm kind of, then this may differ, by the way, according to other statisticians, because there is some debate about statistical inference. But I'm pretty precise about this. When we say you fail to reject the null hypothesis, that is actually logically different than affirming the null hypothesis, because the null hypothesis, remember, is the assumption you make before you test and look at the data. Okay? Now, if you're talking and giving a talk, or perhaps even writing a paper, I don't think I would be so stringent to say the null hypothesis is true, although I might make a note of it in commenting on the paper. But definitely, when you talk about the results, talk about in terms of failing to reject the null or rejecting the null hypothesis. If you write about it in the conclusion and maybe you're a little more loose with your language, I'm probably going to be more forgiving about that, but a lot of people probably wouldn't. I just want to emphasize that. But because in a way, you can say that this hypothesis is consistent, but you can't definitely say it's true, because the true population proportion could be 0.51 or 0.51, 0.26, and 0.23. It could be some other value that's very, very close to what we hypothesized in the null, right? So we haven't proved the null hypothesis. We've just shown that what we hypothesized is consistent. There's nothing wrong. It's not wrong, but we can't really say it's right. And I have to say, again, you're going to read, the more you read even the best science out there in Nature and in Science Magazine, you're going to see, I've read it before, you're going to see people affirming the null hypothesis all the time. But I hope I'm going to emphasize that you don't do that. You're going to be clever, more clever than people who publish in Nature. Isn't that really cool? Okay. Now we go to question 7. And here we actually go to the data at hand. And here we again go to expected counts. And we're going to ask this question again. So now you want to examine people's views toward taxing Wall Street executives. Okay. After gathering a random sample of 200 people, you ask them whether they agree or disagree with the following statement. Wall Street financial transactions should be taxed to prevent casino-style gambling. In your sample of 200 participants, 50 strongly disagree, 100 agree, 20 disagree, and 30 strongly disagree. Okay, so notice what you have here. I want to just key you on this. You have 4 categories. Strongly, agree, disagree, strongly disagree. I'm not even showing my hands here. Okay, just keep that in mind. So if you're going to write the null hypothesis, you have P of 1, P of 2, P of 3, P of 4. When you do a one-way chi-squared distribution test, you're going to have K categories. And you're going to have 3 degrees of freedom, because K minus 1 is 3. Okay, I know I'm telling you more than the question, but just I want to emphasize that in the same way, I guess I want to emphasize the fact that when you're reading a problem, the more practice you get, the more you're going to anticipate the kind of test that is required, the kinds of assumptions being made. It's not required. I want to make sure that's okay for you, but I want to emphasize that there's a lot of information that we already have at hand. Okay, now in the last sentence it says, we think the distribution in the population is 0.3, 0.45, 0.15, and 0.10 in those labels. Now, the other keyword is, or key phrase is, you think the distribution in the population is such. If someone thinks the population in the distribution is such, then this is a clue to us that that you're being set up to test a one-way chi-squared test. Because when you think that something is true, you're not using data. You're actually going along with a hypothesis or a statement about the world. And we're going to use data to see if our statement about the world has a good fit, fits good with the sample. And that's what the goodness of fit essentially does. But we're going to ask you something more simple, which is, what are the expected counts for each category, respectively? Here again, you take each of the proportions and multiply each of those by the total sample. And if you want to test that the numbers you came up with are correct, add these numbers up and they should add up to 200. In fact, they do, right? You have 50 plus, 60, which is 110, plus 90, which is 200. So you also learned something else about the data, right? You know that these categories are mutually exclusive. That is an assumption here, because it's actually one variable. One student asked me, are these different variables? No, they aren't. They're actually different categories of one variable, one column. Keep in mind when you look at the data, when you did the R code, you're looking at one column with each observation having one of, in this case, it would be one of 4 possible categories. And these proportions, that's why we can make these, we can estimate the expected counts and test that we at least did the math correctly if they had up to 200. All right. If you have questions, feel free to fire away. I know we're running a little short on time. Keep in mind that the R code we covered before, and I think we covered those answers. And in a way, I think it's better to cover this right now. So after we run a one-way chi-squared goodness of fit test, we have this with 3 degrees of freedom. Again, it's the same output, but I want to show you a couple things. First, and perhaps most importantly, here we have a p-value that is less than 0.05. So the alpha of 0.05 level, I can already tell you that we can reject the null hypothesis. That what we thought was true in the population is not true. And the fact, when you have such a low p-value, you see our p-value is really at the end of that tail of that distribution, which says that our probability of a false alarm, that is rejecting the null hypothesis when it is true, is pretty small. And that's because the counts, the observed counts here in the top row, are quite different than the expected counts. I say quite different because they're not magnificently different, but they're consistently different enough given the sample size, the degrees of freedom, and the distribution. So I think here, I always like visualization because, especially when you're communicating concepts, this figure here provides what one statistician, Edward Tufte, refers to as an interocular effect. In other words, the interaction between the figure and your eyes clearly show and convincingly show that the p-value is extremely low. Whereas if you look at just the numbers here, you see a string of 1s and 0s that can be sort of mixed up. So if you want to communicate effectively a low p-value that might not be observed, that kind of distribution works. It also helps to show that a p-value that is not statistically significant, but that is still relatively low, if you're going to be flexible and not be so stringent about the alpha 0.05 level, gives you a better idea of of, in essence, how confident we can be about rejecting the failing to reject the null hypothesis. That being said, with a p-value of 0.13 or 14 at the 13% level, I'd still reject the null hypothesis. I still don't think it's true, but a p-value of 0.13 is not as convincing as a p-value of 0.30. You'd see more blue here. That's just to say, maybe there's a chance. There's a 13% chance, right, of a type 2 error, but who knows? The main point here is that hold on for a second. The main point here is that it's okay to provide both of these pieces of information. Just think about whether it's useful to provide and whether you think it helps tell your story. Typically, as I said, when we present statistics, when I write and publish research, I don't provide all of this stuff. I would provide just this text here, and I probably wouldn't even be allowed to print this because a lot of academic journals can't afford to print in color. But I think for research reports, for communicating to decision makers, I think graphics are great. Now, what is our hypothesis in terms of the alternative hypothesis? Well, this is interesting, isn't it? Because if we remember, the null hypothesis is that P of 1, P of 2, P of 3, and P of 4 is consistent with the data. But when we reject the null hypothesis, we have to say at least one of those proportions is not equal to its claimed proportion. It doesn't tell us which one is the culprit. It just tells us the distribution of proportions doesn't fit with the data. The distribution of expected proportions does not fit the data at hand. And that distribution includes at least one of those proportions, but it does not tell us which one. And this is why I often complain about goodness of fit tests, because it's sure, it tells us that as a whole, at least one of these proportions here that we hypothesized doesn't fit, but it doesn't tell us which one. This is why in statistics we often call this an omnibus test. O-M-N-I, bus. Omnibus is sort of on the whole. It tells us as a collectivity, as an ensemble, this distribution doesn't fit. And it's because of at least one of those categories is overly discrepant. Could be all of them, could be two of them. So in that way, the alternative hypothesis is perhaps less satisfying than we'd like, because it really is a better claim, as a claim about rejecting the null than affirming the alternative hypothesis with the goodness of fit test. I know I'm criticizing the goodness of fit test, but I have to say it's quite useful on the whole, right? Because it'll just tell us, it's flexible, I have to say. This is why I like it, because when you have multiple categories and you want to test whether those multiple categories are either equal or consistent with what we think about the distribution of categories, we can make a clear hypothesis test about that. So whether we have 6 categories, 3 categories, 18 categories, we can use one statistical test of goodness of fit. So in that sense, it's pretty flexible, and that's really neat. Okay. All right, it's sort of like it says there's a bad apple here. It doesn't tell us which apple in the batch is the bad apple. There's at least one bad apple here. Now, based on the results on question 8, what is our conclusion? Well, we obtain a p-value of approximately 0.011, which is below the alpha 0.05, leading us to reject the null hypothesis. Consequently, we conclude that at least one of the population parameters is not equal to its claimed proportion. Okay, now we're going to focus on the two-way chi-square test for independence. We focused more on that in the last week. I actually think this is easier to focus on because you'll see it more in practice. If the concept is essentially the same, except we're going to talk about two variables. And we're going to see whether or not those two variables are independent of one another. So we're going to look at some data on essentially what is the ongoing housing crisis. We might have thought it had recovered, but if you go to many cities like Boston, it's increasing. So here's the prompt for this is the second part. Because of the ongoing housing crisis, you think people's views of Wall Street executives might be related to whether they rent a home or not, right? If you're a homeowner and not a homeowner, you might have different views. That's all we're saying. So you conduct several two-way chi-square tests for independence using a random sample of people from a population. You begin by conducting a two-way chi-square test for independence between renting a home or not and viewing Wall Street executives as greedy. You obtain the following results. Now, I want to emphasize this here as well. Here we're using a two-way chi-square test of independence, and we're comparing two categories. Sorry, two variables each with two categories. Now, a chi-square test of independence, as I said before, is flexible. So for a two-way chi-square test, you could actually compare two categorical variables each with three categories. Because again, you're doing an omnibus test of whether or not these two categorical variables are independent or not. Now, if the variables are independent, you would expect the cell counts to be identical in each of these four categories, right? You have people who own homes and don't own home and rent. You have attitudes toward Wall Street executives, greedy or not. So you have four potential categories. If those two variables are independent, then our expected counts in each cell will be identical. That's what independence is by definition. They're orthogonal, they're unrelated to each other. Knowing about renting a home or not tells us zero about whether Wall Street executives are greedy. Knowing about whether someone believes the Wall Street executives are greedy or not tells us nothing about whether they rent a home or not. And that nothingness means that our expected counts in each cell would be the same. So here, just as we did with the one-way chi-square test, what we're doing is we're comparing the goodness of fit between what we'd expect and then what we observe. And in a two-way chi-square test, or what is often just called the Pearson's chi-square test, or just a chi-square test, the expected values are going to be the cell counts in the two-way table, and in a 2x2 contingency table. Okay. Now, if we do a Pearson's chi-square test with these two categories, you see very similar outputs. So you'll see the label is different here. And but you'll see a chi-square test. This is quite low. You'll see a degree of freedom of 1. And then the p-value, that's 0.76. Okay. And then we want to ask you what the null and alternative hypotheses are. The null here is that in the population, the two variables are unrelated, that is, they're independent. The alternative is that the two variables are related, that is, dependent. So, when we do a two-way chi-square test, the null hypothesis is again our expected values. And our expected values assume that the number of counts is equal in the sample. And that's what independence is. So just keep in mind, when you talk about the chi-square test, the null across both the one-way chi-square test and the two-way chi-square test is what we expect. The alternative is a discrepancy from that expectation. So if you can tell, a two-way chi-square test is more common because we're often interested in the association between two variables. And we're often interested in testing whether those variables are independent or not. And that's useful. Notice I'm talking about variables, and because if you have multiple categories, here we have two categories. If you have multiple categories, it doesn't tell us which of those categories drive the association, right? So if two variables are dependent, and we have two 5-category variables, so we have many cells, all we can say is that those two variables are dependent if we reject the null hypothesis and we accept the alternative. It doesn't tell us which one of those categories is really the driver or the predictor of that dependency. That's again, it's an omnibus association. It tests the whole ensemble of categories. Based on the results in question 10, what is the conclusion? Here we state it linguistically, which I think is useful. We move from the equations, or not the equations, but the formal definition of the null and alternative hypothesis, to a statement about it, or translation in language. And we failed in this case because our p-value is less than 0.0. So since our p-value is greater than 0.05, we fail to reject the null hypothesis of independence at the alpha of 0.05 level and conclude that two variables are unrelated, independent in the population. So here's a good example of when you fail to reject the null hypothesis. You're essentially saying the data aren't discrepant from our assumptions, so we can go ahead with our original assumption. And as long as you use this phrase, fail to reject the null hypothesis, you can be a little more loose with your conclusion, which is what I'm trying to say. But you should always frame the hypothesis in terms of failing to reject the null hypothesis. And then you can talk about the conclusion, which is sort of like what you state provisionally in a way about given the rejection or failing to reject the null hypothesis. Because again, when we talk about inferential statistics, we're talking about our best guess, or not best guess, our best approach, best practice toward understanding reality, with the humility and the modesty of understanding that, and the acknowledgement that what we're going to say might not be true. Still, it's all in terms of probability and likelihood. If you're a gambling person, which I hope you aren't, but if you are, where would you place your bets? Well, you're going to place your bets that these are unrelated because you failed to reject the null hypothesis. Okay. Question 12 does essentially the same thing. I'm not going to talk about this in too much detail, except here we have, it's a repeat of the previous concept, except here we have a p-value that's quite low. I do want to emphasize we have a chi-squared statistic that is much higher than before. Before, the chi-squared stat was quite low. We do have a degree of freedom of 1 because our k categories for the variables are, we have 2 here. Right, so we have k categories minus 1. And the correct answer for the null hypothesis is that in the population, the two variables are unrelated, same thing. And we, of course, we reject the null hypothesis of independence at the alpha 0.05 level. And it's useful to talk about the alpha 0.05 level when you say this. I know you'll hear me sometimes say at the 5% level. Sometimes in some disciplines we talk about it, but talk about it in terms of alpha of the 0.05 level. I think it's more canonical, more standardized. Here we have another example in question 14, where essentially we do another chi-squared test of attitudes toward whether or not Wall Street executives are overpaid. The point I want to make here is how do we phrase the alternative hypothesis? Well, we can say that the two variables are related when we reject the null hypothesis that the two variables are unrelated. It doesn't tell us which. Now, if we had multiple categories again, say we had 4 categories, 4 levels in one, four categories in one variable and 3 in the other, We can't say which of the categories drive the relationship, but they are related. And I think another point you could also make is it doesn't necessarily tell you about the strength of that relationship. Keep that in mind. We're talking about statistical significance, not about substantive significance. All right? If you want to do substantive significance, in this case, there are, in more advanced courses, you can talk about other kinds of omnibus measures, like so there's a phi statistic that will give you the general association here. But when you talk about the strength, or you want to talk about interpreting this in terms of substantive significance, go back to the descriptive data and describe the proportions. I think that's part of the story here. Here, when we're talking about chi-square goodness of fit test, it's a test of statistical significance, not substance, right? That's why we're in our null and alternative hypothesis, we're just saying they're related. We're not saying they're greatly related. Doesn't matter how low your p-value is. Based on the outputs, and from question 14, so in this output here, you see that the p-value is 0.25, so it's greater than the 0.05 level. We fail to reject the null hypothesis of independence at the 0.05 levels, since the p-value is greater than 0.05. Now, here we get to what is crucial, I think, or rather, what is relevant to really appreciating the chi-squared goodness of fit test, the two-way chi-squared goodness of fit test. We can expand. It's used to test two categorical variables, no matter how many levels or how many categories there are in each variable. Keep in mind here, you can tell what the degrees of freedom are, because the variable that we use to split up the number of proportions has 3 categories now. So now, instead of having 2 categories, right, which was whether or not instead of looking at renting a home or not, which is 2 categories, those column categories, right, this will be in the columns. We're looking at 3 categories, which is social class. So you have k minus 1, which is 2 degrees of freedom. So even though we have a high chi-squared, now we have 2 degrees of freedom. And we have a very low p-value. When the p-value is very, very low, it's expressed in scientific notation. So if you're not familiar with this is 2.2 times 10 to the negative 16, which means you take 2.2 and then move that decimal point over 16 places. So you have bunches of zeros here. So this would be a case where I wouldn't even bother to really graph the chi-square distribution, because that's such a low p-value. Does it tell you about the strength of the association? No, but it does tell you that we can reject the null hypothesis of independence between social class and the, renting a home and social class. I apologize, between renting a home and social class. In other words, those are definitely not independent. I don't think there's anything else to say here about that, except when we took a look at part 3, we followed that before when we looked at the code. And I do want to emphasize something we haven't covered this week, but if you're interested in exploring analysis of variance in R, feel free to use the toy data set. And I want to emphasize ANOVA, that's what you call it, analysis of variance. It's often used. It's not going to be tested for the final. It's just something that we provide for you that is an add-on, because we can't provide everything for the course. But if you're interested in looking at it and exploring it further, go ahead with it. But it's not necessary for understanding, for really getting an A in the course or excelling on the final exam. But if you have questions about that, feel free to reach out. So we're a little bit over time, but I'm glad we did cover the concepts here. We covered one-way chi-square tests. We covered two-way chi-square tests. And we talked about how to interpret those and understand the null and alternative hypotheses here. And are there any other questions, any other statements? Otherwise, keep in mind, next week, someone had asked, oh, do I record all the sections? Yes, and they are posted, and I will give you information about that. If there's any other questions about the contents, procedural stuff I'll address. But if there's any other stuff related to this material here, feel free to ask. And I understand you don't have to get this the first time. Certainly, I didn't get it the first time. Review, go through the code, and keep in mind next week we're going to cover simple linear regression and inference using simple linear regression and correlation. We're going to combine quite a bit, but we don't have a homework assignment, so that gives you more time to focus on the final project, to meet with me, and to address some of those questions. And that's it. I'm going to wrap this recording up. Thank you very much for attending, and I hope this is helpful. Thank you. So, yes, Lauren, you had asked, sorry, Laura, sorry. Yeah, am I recording all the sections? Yes, they're in fact available via YouTube. We should have the final project examples. And I will post the YouTube here. And what I'll do actually on the course website is I'll post those the YouTube videos on the course website under section modules. But for now, I recommend that you take a look at the YouTube channel, which should, by the way, give you the playlist. And the reason I do YouTube, as I said before, is it essentially provides you with the ability to fast forward and to take a look at things that I think are a little bit more, I don't know, useful or rapid. Sorry, what I meant to say, I was doing some cutting and pasting. There's my YouTube channel. If I get 100 subscribers, I can make a better URL. The reason I do YouTube, as I said before, rather than the course website, is you can subscribe it, you can keep it. It's a resource for you to use in future classes. The R tutorials, we have it on the some on the course website, but I have a whole playlist here of 10 videos that take you from installation, which you can skip if you've done that, to sort of the basic analyses, and I try to make those as playlists. So I haven't posted the last couple of weeks for the sections, but I will do that as well. I'll post those to the course website. What I am working on as we speak is a couple tutorials on a previous section that I did unrecorded, which I regret, which is about the final project, which is essentially the advice I give to students every single time. What I haven't been able to do yet when I spoke with the instructor is whether or not we can actually define what grades the students got from those papers. It looks like those records are, I guess they're lost. We're trying to find them. But in general, they're high A and high B papers. And overall, they're quite good. And I think they're good examples of the diversity of kinds of papers that you can submit for the final project. But again, if you have any other questions, feel free to reach out to me. And if you're one of those whom I haven't reached out to yet, I apologize. I will get to you again. All right. Thank you very much. And I will, yes. You didn't find the final project example postings. Okay. That could be an issue with Canvas. I will talk with the course instructor and make sure we get those up ASAP, and I will send out an announcement for that. Laura, would you like to set up an appointment? Sure. Okay. Why don't you? I want to send this information. Laura, why don't you either text me or use WhatsApp. Okay, I was gonna say you can also use WhatsApp or text me if that helps too. All right, okay, cool. Thank you very much, everyone. And yeah, I'm happy to talk with you and give you as much time as possible that is useful, because I know every project is a little bit different. And I know for those of you who didn't attend the section on the final project, this might be an issue that you want to address. But keep in mind, I'm here for you. And also next week, we're going to cover the material, but we're also going to have extended periods to talk about the final project and the logic for doing it, finding data, doing the analysis. And if you want me to look at your paper, feel free, or go through code and syntax. All right. Have a great night, and thank you very much. Take care. Yes, thank you. Bye-bye.